All right, everyone, let's take a look at some of the homework that we had from last week. 3 sets of it. First one was page 767, number 1 to 7. Second set we had was page 810. And then the third thing we had was worksheet number 24. We'll look at all those separately from one another. Any issues with 767, number 1 to 7? All of these are on Millikan's oil drop experiment, right? Any issues with those questions? 5B? Let's take a look at the whole thing, number 5. Okay, while we're at it, as well. Put it in context. Any others? Just 5? All right. 5A says, what's the net force acting on a charged oil drop falling at a constant velocity in the absence of an electric field? Forget about in the absence of an electric field, in the presence of an electric field, whatever. What's the net force acting on an oil droplet falling at a constant velocity? What's the net force acting on a car driving down the road at a constant velocity? What's the net force acting on anything moving at a constant velocity? 0. 0. It doesn't mean there's no force. There could be a force. There could be 50 forces, but they balance each other out. The net force is always 0 if it's traveling at a constant velocity. That goes back to physics 20, Newton's first law. Object in motion stays in motion in a straight line until acted upon, not by a force, but by an unbalanced force. B says, describe the motion of the oil drop in an electric field that exerts an upward force greater than the gravitational force on the drop. Draw a diagram to show the forces acting on this drop. Okay, so a bit of a tricky question here. We've got an electric force acting up. We've got a gravitational force acting down. And it says the electric force is greater than the gravitational force. Now, the electric force is straight up and the gravity force is straight down. In the absence of that upward electric force, can you tell me what would have happened to this? Can you tell me what would have happened to this, this particle here in the absence of that electric force? It would fall, yeah. If it was moving this way, right, moving to the right, it would have followed a parabolic path, right? If it was just not moving horizontally, then it would have fallen straight down at a rate of 9.81 meters per second squared. If there's an electric force acting up, it's going to counter gravity. In fact, it's going to actually win out over gravity. If it's moving to the right, it will actually experience a parabolic path upwards. Now, the parabola won't be as scrunched together as it was when it was just gravity. Depends, actually. Depends on how big the electric force is. It will be a parabola, however, if it's moving to the right and experiencing those forces. If, however, it's not moving to the right, if it's not moving horizontally at all, then the motion of this is simply going to be upwards, and it's going to accelerate upwards. So it's going to move upwards, and it's going to speed up upwards because that upward force is bigger than the downward force. Okay, make sense? Just like when you jump out of an airplane, there's air resistance acting on you. Okay, upwards, where gravity is bigger downwards, so you accelerate, you speed up downwards. Next set of questions we had was page 810, number 1 to 7, 9, and 11. I told you that number 2 was not assigned, or at least it shouldn't have been assigned to you. So any issues with 1, 3 to 7, or 9, or 11? None? No. No. How many people did 12? All right. If we don't have any questions with that, then we'll give you some answers to the worksheet number 24 that you had, and we'll take a look at a couple of those questions. Take a look at those answers and see if there's any you need gone over. Before you put up your hands, though, and tell me which ones you do need to go over, I want to draw your attention to just a couple of things. First of all, question number 9. I've got that starred. The answer mathematically to what I have on that sheet is 4,4 beryllium. That's not what was intended, however. Think about that. How many protons does 4,4 beryllium have? 4. How many neutrons? 0. You can't have a nucleus with 4 protons and no neutrons. It's impossible. Okay, the electrostatic repulsive force would blow it apart. Okay, it's impossible. It was not meant to be 4,4 beryllium. Rather, it was meant to be 4,2 alpha. The answer was meant to be 4,2 alpha. If the answer was 4,2 alpha, what would we have to do to the question to make it correct? $214 is equal to 210 plus 4. 84 is equal to 82 plus 2. In order to make it correct, we would have had to make it lead 210 with an atomic number of 82. In the question, it actually says lead 210 with an atomic number of 80. That's not even possible. Whatever isotope of lead we have, it's always going to be atomic number 82, not atomic number 80. So it's just a bit of a typo. Yeah, you might not have caught that. If you did, that's great. If you didn't, then you should have gotten an answer of 44BE, even though that's not really, in real life, possible. A couple other quick questions for you before I let you tell me which ones you need help with. What could I have changed this to? 4,2 alpha is exactly the same as 4,2. 4,2 what? Helium, yeah, 4,2 helium. What could I have changed this to? 0 minus 1 beta is exactly the same thing as 0 minus 1 E as an electron. Good. You guys remember from Friday what this thing is? You had two things that you learned about on Friday in that context. This, and you had this. Remember in 1930, this guy named Wolfgang Pauli hypothesized the existence of these particles to account for missing energy. These particles are called neutrinos and antineutrinos. The neutrino is the one without the line over top of it. The antineutrino is the one with the line over it. A neutrino will always be produced along with beta negative decay. An antineutrino will always be produced along with beta positive decay. When you're writing out the transmutation equations, you never have to worry about those particles, those neutrinos or antineutrinos, in terms of balancing them. They have no protons, they have no neutrons, they have no electrons or positrons or anything of the sort. But they should still be there, again, to account for that missing mass. Hypothesized around the year 1930, no direct evidence to support them other than, hey, we need something to explain this missing mass or this missing energy. Here we are 80 years later, 83 years later. We've observed many, many neutrinos and antineutrinos. So we know that, in fact, he was correct. It was just a good theory at the time. Don't forget to write them in whenever you're writing in beta negative decay or beta positive decay. All right, any issues with 1 to 14? You guys ace all this stuff? No issues at all? Good. Guess I didn't need to be here at all, hey? Yeah. Yeah, that's a good question. Let's take a look at one that's an artificial reaction here, okay? For example, question number 14, the last question, is an artificial transmutation equation. And I wouldn't call that alpha decay or beta decay. In the question, I know it said classify them based on alpha or beta or artificial transmutation. 14 would definitely be artificial because it's not happening on its own. Right? We're prompting it to happen by bombarding nitrogen with an alpha particle. Looks like this. 4,2, or 4,7, I should say, nitrogen 7, plus an alpha particle, goes to 17 oxygen. Well, we got to balance this out. 7 plus 2 is 8. Is 9. 8 plus what is 9? 1. 14 plus 4 is 18. 17 plus 1 is 18. Now, that doesn't appear like anything that we've looked at before, alpha, beta, gamma, whatever. So we look on a periodic table and we find that atomic number 1 would be hydrogen. So that would be the product there. We wouldn't call that alpha decay or beta decay, right? In fact, even if it was 4,2 alpha or 0 minus 1 beta, we still wouldn't call it alpha decay or beta decay. We'd still call it an artificial transmutation because we started off with two things on that left side. Yep. I'm sorry? Yes, you could. Yes, that's a good question. Could you call that 1,1H a proton? Absolutely. Just like we can call 0 minus 1 beta an electron, or 4,2 alpha a helium nucleus. A hydrogen nucleus, at least the simplest isotope of a hydrogen nucleus, has how many protons? 1. How many neutrons? 0. So that a hydrogen nucleus is a proton. You'd write that as 11P, right, if you're going to do that. Good? All right. Take a quick second and read through this question and see if you can get the answer to it, okay? All right, guys, how many people got an answer of A for number 157? B, C, D. Good. The answer is D. Now, let's go through this just to make sure that we know why the answer is D. It says we're decaying Americanium-243 via alpha decay. The alpha particle is produced by Americanium-243. It's going to look something like this. Here's my alpha particles generated by this Americanium-243. Before we go any further and figure out what that other element is, we should know what the atomic number of Americanium-243 is. What is it? 95. Look in the periodic table, find that it's 95. 95 plus is equal to 2 plus 93. 243 is equal to 4 plus 239. And when we look at 239, 93 specifically on a periodic table, we'd find that it's neptunium. Now, some of you may have done this question without even writing this out. Just looked at it and said, wait a second, 243 has to go to 4 plus 239, and the only thing with a mass number in our options here is neptunium-239. Therefore, it must be correct. Okay, if you use that logic, that's good. I just wanted to go through all of this just to make sure that if you had two options, neptunium-239 and berkelium, however you say that, 239, you know how to figure out which one it is. Today we're going to talk about half-life. Half-life is the time that it takes, statistically, and I'll tell you what I mean by that in just a moment here. The time that it takes statistically for 1/2 of a radioactive sample to decay. Meaning that if I have 1,000 radioactive nuclei, half of it will decay in a certain amount of time. That time we will call the half-life. You'll be down to 500 of those radioactive nuclei after that amount of time that we call the half-life. Now, the reason we use the term statistically in there is because it's not a perfect science. We make predictions as to how much is going to be left after a certain amount of time. But understand they're only predictions based on statistics, based on the events that have taken place in the past. Now, if we have a big enough sample size, if we have enough radioactive material, then those rules of probability, those statistical laws work out very, very well. If we don't, they don't work out so well. And all the questions that we have will assume a big enough sample size that the laws of probability work out just fine. In other words, the calculations that we make for our predictions will be legitimate answers. Even though, because it's a prediction and because it's based on statistics, we don't really know for sure, even with a big sample size. Now, understand this as well. We're not in Physics 30 just making an approximation because you guys aren't smart enough to do any better. No matter how far you go in physics, you won't be able to do a better calculation than we're doing here today. Radioactivity is a natural, spontaneous, random process. Okay, we can look at what's happened in the past and say, all right, odds are this is what's going to happen the next time. But you can never know for sure because it is that spontaneous, natural, random process. Flip a coin 1,000 times. How many heads are you going to end up with? 500, right? Around that, anyways. Is it possible to end up with 0 heads if you flip 1,000 coins? Yes. Is it likely going to happen? No. No. If you have 1,000 coins, odds are the laws of probability that we've, and the observations that we've made throughout history about flipping coins are going to hold here, and we're going to get about 500 heads and about 500 tails. Okay. If we flip 3 coins, well, all bets are off. Too small of a sample size. If you have 1 million radioactive nuclei, what we do is going to work out just fine. If we have 3 of them, all bets are off. Again, all the problems that we're going to see today and in the future are going to involve sample sizes that are big enough to assume that the laws that we use here, these laws of probability, these laws of statistics, that they work. 2 equations. One equation that you've seen before in Math 30 class. N is equal to n sub 0 1/2 to the little n. You recognize that? Big N stands for the final amount. Big N sub 0 stands for the initial amount. The final amount can be measured in whatever units you want as long as it indicates an amount. For instance, it could be grams, or it could be kilograms, or it could be even a percent, or it could simply be a number, the number of nuclei. A becquerel is a decay per second, so not only a number or an amount like that, but sometimes it can be an amount that's decaying, the rate of decay, a becquerel. Doesn't matter. There's all kinds of other ones as well. Doesn't matter which one you use, as long as you're consistent with N0. Use grams, use becquerel, use percent, I don't care. Use whatever works for you, as long as you use the same units for N0 as you do for N. Now, what does little n stand for? You math whizzes, you. Somebody in my last class said, oh, it's the half-life. Is that right? No. No, little n is not a half-life. Somebody else said, oh, it's the amount of time that's gone by. Is that right? No. Little n stands for what? The number of half-lives that have elapsed. If the half-life of a particular radioactive material is 3 years, and it could be, they range from fraction of a second to thousands of years. The half-life of a particular element could easily be 3 years. Let's say 15 years have gone by. How many half-lives is that? Half-life is 3 years. 15 years has gone by. How many half-lives? What's little n? 5, right? How do we get that? Well, in our heads, we said t over t1/2, the total time that's gone by divided by the half-life. 2 new equations. This one does appear on your data sheet. This one does not appear on our data sheet, but it's really useful to have. So let's remember that equation. N is equal to t over t1/2. Let's take a look at this one, okay? 16.13 on 814 says radon-222 has a half-life of 3.82 days. What percent of this sample of this isotope will remain after 2 weeks? This is going to be our time. Okay, how much time has gone by, our half-life being 3.82 days. I'm going to circle the units there, both days and weeks, not because either one of them is wrong or not because either one of them is even odd. I can use whatever unit I want for time as long as I'm consistent. I just need to circle both of those to remind me to make them consistent. What percent of the sample remains after 2 weeks? What am I looking for here? There's 3 variables that I don't have identified there. It's little n, big N, or big N sub 0. Which one is it that I'm looking for? What percent remains after 2 weeks? Big N. Yes, it's big N. Anybody want to tell me what big N sub 0 is? Got to read between the lines on this one, right? What percent remains, Christine? What percent remains? Well, if we're looking for what percent remains, the initial percent would have been right. So n sub 0 will be 100. When you're dealing with percent, n sub 0 will almost always be 100. You'll be told if it's something other than 100%. All right, n is equal to n sub 0, 1/2 to the little n. We know that n is equal to t over t 1/2. Let's say t is 14 days as opposed to 2 weeks, and t 1/2 is 3.82 days. That gives me 3.6649 half-lives. Now, we plug that into this expression, 100 times 1/2 to the 3.6649. I'm going to bring up the calculator here and make sure that you guys can follow along with this and get it correct here. Let's say 100 times 0.5. Careful here, it's not 0.5 times 10 to the 3.6. It's not scientific notation. It's 0.5 to the 3.66. 7.88%. Boy, after 2 weeks, most of it's gone. Why? Because the half-life was pretty small. It was only 3.8 days. Half of it was gone in 3.8 days. Half of that was gone in another 3.8 days. Half of that was gone in another 3.8 days. So by the time they get to 14 days, we're left with not much left. Okay, give these 2 questions a try, please. All right, everyone, if we're not having any questions with these problems here, let's take a look at the next example, which isn't in your textbook. Rather, you're going to have to write down. It says, the half-life of carbon-14 is 5,730 years. Remember that number, or at least remember where to find that number, because there are a couple of questions later on that you're going to have to do that require you to know the half-life of carbon-14. 5,730 years. How long does it take? How long does it take? That's going to be T that we're looking for 12.5 kilograms of carbon-14, that's going to be my original amount, to decay into 400 grams of carbon-14. That's going to be my final amount. Now, I'm going to circle the grams and the kilograms, not because they're both odd units, or not because either one of them is odd units in this context, but simply because I got to make sure that I'm consistent and use either grams or kilograms throughout the question. The only equation I know here that has t in it, which is what we're looking for, is this one. N is equal to t over t 1/2. Rearrange it to solve for t, it becomes t 1/2 times n. T 1/2 is 5,730 years. N, we don't know. So let's use our other equation to solve for little n here. N is equal to n sub 0 1/2 to the little n. We know what n is. We know what n sub 0 is. How do we solve for little n here? Well, there's a couple of ways. One way that you've learned in math class, and that will work every single time, regardless of what the value of n is. Another way that will work if n is a whole number. And for us, in Physics 30, n will be a whole number. The curriculum objective that's mentioned in the program of studies for Physics 30 says exactly this, that you need to perform simple, non-logarithmic half-life calculations, meaning that you're never going to have to use logarithms. There's always another way. But it's not saying that you can't use logarithms. In this question, logarithms, if you're comfortable and familiar with logarithms, may be a bit of a shortcut and maybe speed things up for you a little bit. But it's never a requirement. Let's do it the other way first. Then we'll go back and solve it using logarithms. After 0 half-lives, how much do I have left? 12.5 kilograms, right? After one half-life, I have 6.25 kilograms left. After two half-lives, I have 3.125 kilograms left. We keep dividing by 2 because half of it keeps disappearing within each half-life. After 3 half-lives, we have 1.5625 kilograms. After 4 half-lives, we have 0.78125 kilograms. And finally, after 5 half-lives, we have 0.3906 kilograms. Now, 400 grams is 0.400 kilograms. That's not exact here. Okay, we've gotten down to 0.39 kilograms, but it's real close. In other words, how many half-lives have gone by during this time that it decayed from 12.5 kilograms to 400 grams? Almost exactly 5 half-lives. I suspect that any question that you see on a test will involve exactly 5 or exactly 3, a whole number of half-lives. In the event that you get something like this, where it's not exact, it's not perfect, go with the closest number. That answer will work for you. So we multiply 5730 by 5, and we end up getting 28,650 years. Now, we want to solve for a little n the other way if you're comfortable with logarithms. This will give us an exact answer, but in the event that the answer that we just got and the answer that we get using logarithms are slightly different, both answers would be accepted because they don't require you to use logarithms. Here's how to solve for a little n. It's log n over n sub 0 over log of 1/2, or log of 0.5. So we're going to say log of 0.4 over 12.5 divided by log of 0.5. When we do that, we should get, I believe it works out to be something like 4.98 or something like that. 4.96. 4.96. That's not exactly 5. And because of that, we're going to get a slightly different answer when we multiply 5730 by 4.96 than we are when we multiply by 5. As I said, you get a question like this on a test, either the number n will work out to be the exact whole number, or both answers would be acceptable. Okay, if it's multiple choice, you're not going to get 2 answers that are close enough together that you're going to be forced to pick between them. Okay, it'll be clear which one is the answer. All right, I'm not going to give any questions on this quite yet. I'm going to go over a couple more quick things for us, and then we'll give you some questions to work on to finish off the class here. The next thing that I want to look at is still radioactivity, still half-life stuff, but specifically a graph involving half-life. Anytime you see a radioactive decay curve, every single time, no matter what the element is, the basic shape of it will look like this. It will be exponential decay. Now, the good news is there's only 2 things that you've got to be able to do with this graph, and neither one of them are very hard. Both of them are quite a bit easier than the analysis that we've done on graphs up until this point. We need to be either able to find a time, or we need to be able to find an amount, in this case the mass. If we want to find a certain time, then we're going to read over and down on the graph. If we find an amount, it's going to be up and over. For instance, what's the half-life of this radioactive sample? What's the half-life of it? Well, the half-life is a time. We start with 100. After one half-life, we go down to 50. Let's go over and down. After one half-life, it appears as if, after we've gone down to 50% of what we started with, it appears as if it's taken about 2 years. So the half-life here would be 2 years. We want to find any time we're going to go over and down. If we want to find an amount, like for instance, how much remains after 5 years, then we're going to go up and over. How much remains after 5 years? About 25 grams. It's either going to be over and down or up and over. The only way we could do any calculations with this graph would be to introduce logarithms, and it wouldn't be pretty. Even for people that are okay with logarithms, the analysis of this graph involving calculations would not be fun. Finally, I want to talk about one application of radioactivity here today. It's called radioactive carbon dating, or just simply radiocarbon dating. Our atmosphere consists of a number of gases, including carbon and nitrogen. There is much more nitrogen in the atmosphere than there is carbon. In fact, nitrogen is the most plentiful element in the atmosphere. Nitrogen, when bombarded with cosmic rays that include neutrons, can actually change, however, into carbon, but not carbon-12, not the most common isotope of carbon, but rather carbon-14, which is a radioactive isotope of carbon. This happens all the time. It happens continuously in the Earth's atmosphere. Plants breathe, for lack of a better term, plants breathe carbon dioxide, they ingest water, they use sunlight to produce oxygen and glucose. Photosynthesis, right? When they ingest carbon dioxide, that carbon dioxide consists of carbon-12, at least mostly carbon-12, because that's the most plentiful isotope of carbon, but also a little bit of carbon-14. Therefore, every living plant is slightly radioactive because it's consuming this radioactive carbon-14 a little bit in very, very small quantities that was generated in the atmosphere when neutrons collided with nitrogen-14. Now, that radioactive carbon-14 decays. As that radioactive carbon-14 decays, you would think the amount of radioactive carbon-14 in the living thing would decrease, but it doesn't, because that living thing keeps ingesting more carbon dioxide, which replaces the radioactive carbon-14 that is decaying. The amount of radioactive carbon-14 relative to the amount of carbon-12 remains pretty constant over the life of a plant, remains remarkably constant over the life of a plant. There are small fluctuations, but for the most part, it remains the same. Now, as soon as that plant dies, the carbon-12, nothing changes. It stays in this living thing, or this dead thing, in the same amount that it was in when this plant died. But carbon-14 doesn't. As soon as the plant dies, the decay keeps taking place, but the replenishment doesn't, because it's no longer ingesting carbon dioxide. So you can imagine where this can be useful. If we know how much carbon-14 is present or should be present in a living plant, and we look at this dead tree over there and say, oh, wait, there's only this much radioactive carbon-14, we can compare N that we just measured with N sub 0, the amount that it would have had when it was still alive, to determine not how old the tree is, but to determine when the tree stopped replenishing the carbon-14. In other words, when the tree died. It's a remarkably accurate way of aging things that were once living, including plants, because they ingest carbon dioxide, but also including animals. Why animals? Animals don't breathe in too much carbon dioxide. What do animals eat? In Alberta, we eat cows, right? But what do cows eat? Grass, plants. At some point, we all go back to plants. At some point, we're all, somewhere down the chain, herbivores, right? We consume plants that have this carbon dioxide coming in with carbon-14 constantly being replenished. So if you find a body that, is some native burial ground or something, you can determine how old that is as well. Not how old the person was, but how long ago the person died based on how much carbon-14 is left versus what should have been there when the person died. Make sense? Anybody explain to me briefly, and this is a question in your check and reflect that you're going to get in just a second as well. Anybody explain to me briefly why it is that you can't use radiocarbon dating to date really, really old things? It works for, something that's 5,000 years old. It worked for something that's 1,000 years old, several thousand years old. But you can't radiocarbon date a dinosaur bone. Why not? Yeah, too much carbon has deteriorated to get an accurate measurement of that age, right? Remember what we said when we first started this lesson here today? We said, this stuff only works. This whole idea of statistical analysis with it only works if the sample size is great enough. If you look at something that's 5 million years old, the amount of carbon-14 that remains is so small that the sample size isn't big enough to assume the statistical analysis works. So we have to deal with something that's, 1,000 years old, a couple thousand years old, 5,000 years old, 10,000 years old, 5 million years old. No, it's pretty much all bets are off. There's got to be other ways. I'm not sure, to be honest, what exactly you'd use, but it wouldn't be radiocarbon dating for sure. If you had something with a half-life that was much, much greater than 5,700 years, you might be able to do that. But I'm not sure if there's anything like that that would go.
So how do you know how much they started with them?
Well, biologists, scientists would know that each living thing has not a certain value of carbon-14, not a certain amount of carbon-14 in your body, but a certain value relative to the carbon-12. Does that make sense? So, somebody else, what do you weigh? About 150, 160? 140? Okay. You weigh 140 pounds. Somebody else that weighs 300 pounds is going to have much more carbon-12 in their body than you are. They're also going to have much more carbon-14 in their body than you are. But they'll have the same proportion of carbon-12 and carbon-14 in their body that you will. Does that make sense? Now, when you die, your amount of carbon-12 won't decrease, but your amount of carbon-14 will decrease, so your proportion will go down. But if that 300-pound person is still alive, his proportion won't go down. Does that make sense? So we know not how much carbon-14 that you're supposed to have, but we know the proportion of carbon-14 to carbon-12 that you're supposed to have while you're living. Okay, and that remains relatively constant. Right? Okay, that's it for today, other than a few check and reflect questions on 817. I'd like you please to take a look at page 817, number 1 to 9, except for question number 2.